our first speaker. And our first speaker is Jelena Ćalić.
Yes,
I hope
here I am.
your name correctly. And
yes, it's correct. Great.
you know why it's correct? Not because I knew it, but because Amber cheated and got you to say it, and then she told me how to say it.
Okay.
Jelena is a research associate at the Geographical Institute of. Now, this is a name I cannot pronounce. Dr.
Jovan Cvić.
Cvić, okay.
Yeah, you know, the founder of karstology and etc.
You know, I know that, and I could never say his name. But I see here you are a Karst admirer since childhood and a caver since 1996. So
yeah, that's right.
That's very good. So Jelena is going to talk about stripe karst tectonic settings, examples from Eastern Serbia. So we can see your screen and it looks good.
Yeah, is it, you see everything?
Yes.
Is it
I
okay?
can see everything, yes.
Okay. Well, fine, thanks. As you know, my name is Jelena, I'm from Serbia, and I want to thank the organizers for all the efforts for putting all this together. And I will be telling some interesting things about our stripe karst in Serbia, and you can see my co-authors. We are all from different various organizations, but we are all cavers, so it's always holding us together. Okay, so at the beginning there is some theory about the contact karst versus stripe karst, which is the relation. So it's actually set and subset. So contact karst is related to lines of contact between karstic and non-karstic lithologies, and it is characterized by strong allogenic impacts from non-karst to karst. And the types of contact karst were elaborated quite well by Ivan Gams back in 1974. And it included morphologic and hydrologic criteria, and also by Ford and Williams in both issues. And this subset, which is stripe karst, it is defined as the author of this concept, Stein Erik Lauritsen, defined it as an end member in the contact karst spectrum, which means that the relation between length and width must be below 3, and the best stripe karst would be if that gamma is over 30. So we will see what we have. First, we just introduced the setting. So this is the Balkan Peninsula. Serbia is part of the Balkan Peninsula. You see southeastern Europe, and Serbian karst comes in two great belts. So on the west, it's Dinaric karst, and on the east is Carpathian Balkan mountain range, which is partially karstic, but all karst areas are scattered and are not very compact. So we have hundreds of kilometers of contact. And our case studies, first we will show, I will show Jevrinska Greda, it is here. Then the mountain range of Krš, which is one of the words for karst. And the third one is Kamenica karst, close to the Bulgarian border. Just to make some geological introduction or broader geological setting. So these are the Carpathian Balkan mountains, and there is a strong pressure from the west. So that's why the Carpathian Balkan Mountains are somehow over the, they are like surrounding the very, very strong and rigid Maesian plate. So Maesian plate is an old European plate, very stable. And you can see the activities, the activity of these fault systems which surround, and these are some of the most important is Timok fault, and all of them are dextral strike slips. And our first example is Jevrinska Greda stripe karst. I like to call it my snake because it's really so thin and long. So in black are limestones, and another eastern part is flysch, and western part is schists. And this stripe karst fits all the requested proportions. And this is just a very simplified sketch of the ridge evolution. There is a great system of naps overthrusts in eastern Serbia. So first on the autochthone, first the flysch nap was transported, and then so it is in opposite way, in opposite sequence than usual. And after the activation of Jevrin fault, Jevrinska Greda karst was upthrown, and now we have this situation. So just to see where are we in tectonic sense. So the whole western contact is tectonic contact, and there is a large input of schists to all the caves. While on the eastern contact there are not so many caves, and you can see this that on this overview map. You see that numerous spawners are on this side. And this is a bit of close-up on the widest part, and you see that along the fault situated ponors. This is the larger cave, a bit less than 4 kilometers. It's under survey still. And here we can explain what is the most important for this subject. It's the movement pattern of the Jevrin fault. So the older movements which uplifted the limestones were predominantly vertical, and later on that movement somehow slowed down, and there are younger transcurrent or strike slip movement, as I mentioned before, the characteristic for all eastern Serbia. So here is one set of joints. There are 3 general directions, and it is interesting that the most numerous joints are perpendicular actually to the fault itself, but they are very small. So only in some outcrops you can find small areas, but they are numerous. And on the other hand, along the main movement, there are not so many, it's not so visible, and not so many visible faults, but they are generally the dominant in terms of significance. And this is one of these faults in the Momačka Pećina, which is well, quite impressive. Not so many of these. So it is the brief presentation of this first site, the first case example, and we move on to another case examples, just to show. So this was the first, and we will show these again, the same pattern. So another is the example of Karst Mountains, which actually is a long mountain range with several units, with a combination of Jurassic and Cretaceous limestones. And here you can see some characteristics of these stripes, which are one by one doesn't have very high values, these gamma values, but altogether, when we count 43 kilometers of length and average width of 1.5, this is quite a good this coefficient. And the important thing to stress is this bore fault. We will see it on another slide, and it is also in the similars. It is practically in the system with the most important Timok fault. So you can see here the many contact features are on these northern portions, while the southern portions are almost isolated karst in terms of gums. Okay, and here is a photo of the southern slopes of Mali Krš, one of the components, and here is a proximate trace of bore fault. And it also follows the same pattern, and all of them with their movement mechanisms cause the elongation of and small thickness of limestones, leading to the development of stripe karst. Here are some measurements. The measurements were done in the cave called Fufa. It is in Mali Krš limestones, and you can see one of the faults striking north-south with dextral movement, of course, and also the striation of this another fault plane indicating also the dextral movement. And here you have the strain axis. I would not go into details, but you can see that the highest strain is here along this direction. And finally, the third example, which is Kamenica karst close to the Bulgarian border, I have to deeply apologize because it was supposed to be the southernmost of these case studies, but due to some organizational problems during the last spring, we couldn't make it to do the field study. So we just see that the area is also positioned along and some insignificant faults, and the proportions of karst stripe are also fitting into the model, and we can just promise that by the time of publication everything will be fixed, and we are planning this autumn to go to the field, so we will be able to do all the other measurements here as well. And with this beautiful panorama of Veliki Krš mountain, I would like to thank you for your attention.
Thank you very much. I don't think we have any time for questions right now. I took too long introducing you, so I took some of your time, and I'm sorry. But if anybody has any questions, go ahead and put them in the chat, and then we can get them to the presenters as they come. Our next presenter is Tunde, and Tunde, I'm going to take you up on your offer about just calling you Tunde, okay? Because I heard your recording.
Yeah, it's okay.
Tunde is a PhD student in the Karst lab of Professor of Dr. Andreas Hartmann at the University of Freiburg. He works on database development, large data set analyses, comparative hydrology with focus on recession analyses of a large number of karst spring hydrographs. So it sounds like you're doing a lot of statistical analyses. So the title of his talk is A New Approach for Automatic Extraction of Karst Conduit and Matrix Recession Coefficients. So if you're ready, take it away. I want to share your screen. There you go.
Yeah. So I hope you can see my screen now.
Yes, we can see your screen.
So thank you very much, Pat, for the introduction. So my name is Tunde, and I work as a PhD researcher at the Chair of Hydrological Modeling at the University of Freiburg in Germany with Andreas Hartmann. And today I'm presenting about our effort to develop an automatic karst recession extraction method. And it's already 7 p.m. in Germany, so it's actually dinner time, but I'm very glad to be part of this presentation and to give update on what we are doing. So in the plenary session, I listened to a lot of people talking about caves. I'm not a caver. I'm a geologist in my background, and I'm more into groundwater modeling and uncertainty analysis. But we all know these caves are very important. Karst is very important. Karst aquifer supplies drinking water to a large proportion of the global population. And we all know that it's very complex with the flow between the conduit matrix interactions, and it's also it can also be very vulnerable. So all this put together, that means we need an in-depth understanding of the karst aquifer system, how the groundwater flows and interacts. And by this, we should be able to have some kind of quantification, estimation of these drainage parameters. For example, in terms of vulnerability, in terms of pollution, if we have these kind of parameters, we'll be able to do a kind of temporal mapping on the pollution, transport, and the rest. So these parameters are actually very important, and also for water management, and most importantly for model development and model improvement. And that is why we are actually working on this global objective approach for karst recession. And so, as we all know, karst spring hydrograph and recession is the receding limb of the hydrograph, and this part can be divided into different components, like into mostly 2, depending on how you want to see 2 or 3 parts. The fast flow component, which is the component just after the event, and the slow flow component, which is the part when the spring recovers back to base flow. So if you want, you can also have the mixed component, which is the mixture of the conduit and the matrix drainage flow. But for this study, for this presentation, I will not be talking about the mixed component. I'm focusing more on the conduit, the fast flow, and the matrix and the base flow components. And traditionally, if you have a spring hydrograph, we would separate this component by having a semi-logarithm plot of the recession hydrograph, and we would manually feed a linear line to the base flow to extract the base flow recession, and the other part would be the conduit flow recession or the fast flow recession. And then we feed appropriate storage outflow model, popularly used model Margin or Marley equation, to extract or to estimate the recession parameters. And if we have additional information about the physiochemical properties, we can also use electrical conductivity to actually separate the conduit and the matrix flow, because during peak flow, during conduit flow, we have dilution of EC, and then we have this kind of shape, and then after the base flow recovers, we have more stable plateau in the conductivity. So our major objective then, because this is, as I explained earlier, you fit the manual line, then you do this manually and subjectively. So our objective is then to use the popular or the range of recession extraction method developed for stream flow recession, and see if they work for Karst spring recession, and see if they will be able to identify the separate components of the Karst recession and compare their performances. And at the end, we want to develop an automated objective procedure that could estimate Karst conduit and matrix recession parameters. And if we have this kind of procedure, that means we can apply this procedure to a large data set like we have in the workers database, and we can estimate we can have an estimation of global recession parameters in different regions or in different scale. And this will be a useful plugin for our model, like for example, Richard model and every other model that estimates global water balances. And then with this will be a very important tool that we can use for global large dataset analysis. So therefore, we select two popularly used recession extraction methods for stream flow, the Bootstrap and the Vogel method. So I should mention that this presentation I'll be talking more about the methods, and I will be very brief with the results. So the Bootstrap method these both methods were developed for stream flow recession analysis. And what the first method do, the Bootstrap method, is that they only select the declining parts of the hydrograph. That means it's slope-based. And then they remove some parts of the hydrograph of the recession segment. That is, the first 3 days are removed just to avoid influence of surface runoff or superfluous flow or malicious flow. And then all they remove 4 days if you have a major event. So what is major event? It was not defined, but for this study, we have used a percentage of exceedance of 30% as major event. And then the last 2 days were also removed. And also, if you have a sudden change in DQ of 2 successive flow, you also remove them, because they think also this is too sudden. I mean, if you have base flow, everything should be smooth and not like sudden change in DQ. So it's removed. For Vogel as well, for Vogel method, you have first like we smoothen the curve with 3 days moving average, and then the first 30% of the segments extracted are removed. For example, after smoothing the curve, if I have 10 days of recession, then I remove 30%, 3 days of the recession, and then the difference between 2 successful recession events should be less than or equal to 30%. So if it's more than 30%, then these points are also removed, because they also only want to extract the base flow component. So these restrictions, filters, and exceptions, they are actually imposed there to remove superfluous flow or quick flow or first runoff contribution, which in Karst hydrology would actually mean that we are removing the quick flow component of the Karst spring recession. So to have some kind of comparison, we also compare the classical approach, which is the manual fitting of the curve. But here we try to do it automatically by firstly applying the 3 days smoothing average to smoothen the curve, and then we fit a simple linear regression model to the recession segment iteratively. So for example, so we fit the segments with simple linear model. So if the R square is less than 0.5, then we remove the first point, then fit to the rest of the points. If it's still less than 0.5, we remove another second point and fit the rest of the point till we have an R square of 0.5, where we consider we have a linear model, which is more representative of having a base flow. So now we have these three extraction methods. I wanted to put that in mind. And then the recession analysis model. So we use the popular margin model because it's more popular and being used. I'm sure we all familiar with this margin model where we have the base flow component and the quick flow component. So I don't want to say so much about that. And then we introduce three variations of this margin component. And the first variation, which is the M1, would be how you would normally fit the margin model by firstly fitting the base flow component to the extracted base flow segment. And then you fit the entire model to the entire recession segment, which is the standard way of fitting it. And then we thought of, because in this approach, that means you predefine the TI, and then by that you predefine the M. Then we thought of why not having a bit of freedom for the M. The model should optimize the M by itself. Then we have the second approach where the predefined M is not used. Then we fit this base flow component first, and then we optimize these three parameters with the model. And the third approach is where we actually give a lot of freedom to all the parameters in the model by optimizing all the parameters. So this has more freedom. It might be a bit of over-parameterizing the model or over-fitting the model, but we just want to see our results. So now we have three extraction methods and three derivations of margin model that we all know. And then we apply them to three catchments, springs in Austria, Switzerland, and in Lebanon. We have the snow catchment and humid catchment and the Mediterranean catchments. And all these data sets, they are in daily or daily resolution, and they are available on the WCAS database. So if I move on, I just want to show how this extraction method, the Vogel, the bootstrap, how they work with the restrictions and without the restrictions, all those filters they remove. So example is this. So this is the bootstrap method where it's slope-based, you remove 2, 3, 4 days. So with the restrictions, you will have this. That means you have only the base flow. But if we kick out all those restrictions, we have this. That means you are able to also extract the conduit flow. And this part will be the base flow. And the beginning of the base flow, the end of the beginning of the base flow is where the quick flow ends. That will be the TI in the margin model. And then the Vogel method as well, the similar thing with restrictions and without the restrictions. So I'm not showing the classical method because of extraction, because we all know this and because of time. So in general, so this extraction method, we're able to extract different number of segments. The bootstrap method, which is the more strict method, extract less segments. And the classical, automated classical method and the Vogel method extract almost similar number of segments because they are based on the same theory, this moving average to smoothen the curve. And then a brief overview of the results. It's a lot of segments. I just chose this segment to show. Not all the segments gives good fitting like this, but this is one of the best. We also have some with like really profiting. So just now I'm showing just the M1 and the M3 combinations with the three extraction methods. I omitted the M2 because of time, and I'm just showing to these two extreme variations. As we can see that the alpha parameter is actually more or less consistent amongst all the methods. But the eta and the epsilon parameter, it's a bit slightly varies among the methods, which is actually due to the varying initial conditions determined or specified by the different extraction methods. So that is why these other parameters actually varies. But in general, they perform well, and the TI, it's actually the end of the conduit, the solid line, end of the conduit with the M1 model where the N is predefined. And when we optimize all the parameters, we have a different TI, which is the red line in dash. So this shows like a bit of variation between predefined TI or if we optimize it. Not so much variation except for this, but it shows that these methods are capable of extracting Karst conduits and matrices automatically. And then this is a lot of information here, but I'm focusing on just one of the methods which I see that actually works well, which is the Vogel method. We can see because this is the method that I actually see that it gives less uncertainty for the parameter distributions across different range of catchments, as we can see from the box plots, which are more narrower compared to the other ones. So the Vogel method shows more promising potential of being useful for the purpose in Karst recession extraction for automatic analysis, and compared to the other two methods. And if you look also, the M3 approach, which we have large degree of freedom, actually have a bit of tendency to of having larger uncertainty, especially with the alpha and the eta parameters. So this could be due to a lot of freedom that we give to the model, or maybe it's the reality, we don't know, but it's one of the questions we still want to answer in our future study. And then we evaluate the efficiency of the model, and we see that, okay, every model performs really good combination of the extraction method and the variations of margin model, although the M3 shows higher, we have this trend, the M3 is more better than the M2 and the M1. So that means with more degree of freedom in the model, we have better results. Does it mean that we are over-parameterizing or we are over-fitting the model? We don't know. These are one of the still questions we still want to answer, whether we are over-fitting or we are over-parameterizing the model with the M3 method. So these are one of the future questions we are still trying to answer. So in conclusion, so the traditional methods actually do not capture the entire Karst recession periods, but if we adapt them, remove all those restrictions from them, they are actually very useful and they are very promising for us to develop an automatic recession extraction method. And for example, the Vogel method shows very promising results and it could be very useful. And also because we just tried this method, we still need to validate this method. So we are still looking at validation approach, like using physiochemical parameters, like electrical conductivity, if it's available, which is not always available, as you know, to validate the methods if it actually works. And one important thing would be to actually quantify the uncertainty associated with varying initial conditions and conduit matrix factor contributions, which we see that this is the major thing, because at times with normal optimization, we have problem with equifinality, whereas different parameter combinations result in similar results. So we have to quantify this uncertainty, especially with how much contribution do we have from the matrix at the beginning and so on. So this is what we are doing, and I hope that in subsequent months we will achieve better results. And we have a publication going in press, and we have a publication going on these methods and approach. So thank you very much.
Okay, thank you very much. I do not think that we have time for questions right now. We're a little bit behind. But, once again, everybody could submit questions if you have some, and we will make sure that the speakers get those questions. Our next presenter is Dr. Derek Ford. And do I really have to introduce you, Dr. Ford? Anyway, he has extensive experience in karst and cave geomorphology, hydrology, and speleothem studies. I like to think of him as the godfather of cave science here in North America. And
so sometimes get a bad word.
No, that's a compliment. So his topic is going to be the Mahony and Tunago adjoining but contrasted karst plateaus in Canada.
Okay, I'm waiting for the screen. Oops. Oh, there we go. Good afternoon, folks. For the past 20 years, I've been doing a lot of work mapping in a preliminary fashion karst phenomena in the Northwest Territories of Canada. I'm going to show you three distinctly different areas from the eastern extremity of the limestones and dolomites today, where they lap on to the Canadian Shield, Precambrian and generally insoluble rocks underneath. Next, please, Autumn. Here we are, we're up in the, can you see my signal on the screen? We're up in the Northwest Territories. The Mackenzie River is the core to the west. The enormous Mackenzie Mountains, where I've worked on 2 major national parks, and the further Franklin Ranges to the east, and then nearly flat-lying rocks along the edge of the Canadian Shield here. And today I'm going to take you into that region. It's a region that during the last glaciation was buried by the Laurentide continental ice sheet. We're up there. That's the position at 10,000 years ago. We're 65 degrees north and up to 500 meters above sea level, so that the mean annual temperature is around about -7 to -10 degrees Celsius. Leaky permafrost prevails. Can you give me the next screen, please, Autumn? I just put this one on to show you the comparison at true scale between the karst in the region I'm looking at, there's more down here I've not put on, and the karst of the British Isles. They're roughly, the karst on the mainland of the Northwest Territories is roughly equal in area to the karst of the British Isles, just to give you a scale. Next, please. Here's a picture of the tectonics. There's the Mackenzie River down the middle. Tremendous activity due to plutonic injections in the Cretaceous to the west, immense overthrusting nap structures coming up to the last major thrust here, and then we have undisturbed limestone to the east. I'm going to show you 2 patches of undisturbed limestone adjoining one another, and then we'll finish up at that most easterly of the Great Cretaceous thrust. And we're going to this region here, and as you can see, geomorphologically or karst morphologically speaking, it's pretty busy. Next slide, please, Autumn. Here's the host rock for the first 2 sites, the Franklin Mountain Formation. It's Ordovician in age. It's a nice Sabkha facies, about 400, platform facies about 400 meters thick. We've got very nice regular dolomite with good vugs in it, and a lot of chert nodule. Clearly the late stages of glaciation were loaded with water, so that there's not much till, residual glacial material, other than the essentially insoluble chert nodules. You see them piled up on the edge of a sinkhole here. Next one, please, Autumn. So the first 2 sites are north and south of a giant spillway. Ice had receded to the western arm, the Smith Arm of Great Bear Lake. A major river poured out, created this channel, 1,000 to 1,200 meters wide, 120 to 150 meters deep. On both sides of the channel, spring into the spillway, creating lakes, and then the Hare Indian River here. And we're going to start off by going to the Mahony Dome first, south of the spillway, and then the Tunago Dome, north of the spillway. The Mahony Dome is a scarp sloping, we're dipping westward. We go up to 480 meters above sea level. The Tunago Dome is somewhat gentler, dropping away to the east. Next, please, Autumn. This is the Mahony Dome, why it was described like that. Beyond, that's the Smith Arm or west arm of Great Bear Lake in the background, till dragged out of the bottom, muds and clays dragged by the glaciers, piled up against the dome here, ponds on them. There is the spillway. This is this beautiful domal feature. It has springs around the sides and major springs in the spillway, the hydraulic gradient being favorable for it. Next, please. I've seen a lot of what biogeographers and biokarst, surface karst folk call alvers. It's a Swedish name for the island of Gotland in southern Sweden. This is the core of it. It is an impoverished planting on ice-covered, or rather permafrozen soils. Next, that's the core of the dome. As we move away from the core, you see what it's like, very thin soil. Hydraulic gradients lateral to springs around the dome begin to increase, and we see the dome begin to be drained by these sinkholes. This is one that we put down on, plenty of residual mud in it, but look at the contrast between this vegetation and the green, the rich greenery of the well-drained topography there. The permafrost is thawed at the sink point. Next. There are many glacial scours on the dome, shallow ones, and each of these is tends to be occupied by a small lake that hydrologically, to a considerable degree, functions like a polya. Here's one that obviously fluctuates a bit seasonally in its elevation. You will see there's a sink there and there's a collapse sink ponded over there. Next, please. As we get closer to the spillway, it's in the background there, you can't see it. These elongated polya-like features drain, and they only flood seasonally. Here's the one record of a seasonal flood, and you see how sharp it is. There's the mean temperature coming up in the analytic year 1976, above the freezing mark, and then back down below. Just after the thaw begins, whoop, she comes and down she goes. It's a flood zone, and this is the scene in the bottom as a small stream is flowing later in the melt season. Next, please. As we come closer to these spillways, the hydraulic gradients increase again. These polya-like features are fully drained. You can see shrub tundra and trees beginning to advance, and sinkholes developed in the bottom of the former polya. You can call it a ponor if you like, that are flooded seasonally and remain very wet. Next, please. I just got a message from Windows, and there's one sinking stream. Bob Van Everdingen and a hydrogeologist studied it. It's about 330 meters above sea level. It drains to springs at 184 kilometers away. It's a very nice, pretty picture going straight down a major joint line. Next, please, Autumn. Now, where we were was over here. Remember, I showed you the ponded mud and clay of the Mahony Dome. We see similar topography when we come to the north of the spillway. There's the spillway for over a little bit of ground, but then we see a distinctly different topography in this region here. This is Tunago Lake. This is obviously Google Earth. And what you've got to imagine is still covered by ice. The ice front is receding, and the biggest river you can ever imagine, it's the Yokalaupa glacial burst, comes straight through that sector there and wrecks a perfectly respectable platform karst. Next, please. Next. This is the picture we started off with. This is a limestone or dolomite pavement karst, a clint and grite structure. But most of the clints have been swept away. They were swept away in this Jokkelaub, or scabland flooding. It's a scabland topography in the around the Tunago Lake because of this great glacial outburst. Next, please. Do you see these sinkholes are, which is what they're functioning as, develop in a distinctly different way. They're formed as scour holes. Imagine a big boulder in the channel of a sandbed river. In flood, water piles up behind the boulder and scours a deep depression there. That's exactly what has happened in each of these cases here. Every one of them is functioning karstically. They're all draining down through a thin veneer of glacial sediments into the dolomite underneath and draining to the spillway or to Tunago Lake. Next, please. Autumn. So I've showed you Ordovician regular flat or slightly dipping Ordovician limestones, two topographies. Now I'm bringing you to the thrust line west of them, and this is the form of the thrust. The bare rock formation of Devonian subcophaceous dolomite and anhydrite was thrust over the dolomite in the two domes. The hydration of the anhydrite beds occurred when subglacial water was forced into the eastern thrust margins during the melt of the ice. Remember that hydration causes a volume expansion that can be as great as 30%. This great ridge here on the edge of Lac Belleau there is 800 meters wide, 200 meters high. You see the dolomite, it's a mixed fashion, facies, remember, the dolomite coming up, dipping down again. It's just a giant uplift and rupture. There are several hundred kilometers of these ruptures in this region. Next, please. I brought you, we were working in this region here, east of the thrust. Now I brought you and introduced you to this thrust. This is a picture of Lac Belleau. It's about 300 square kilometers in area and 255 meters above sea level. North of it here is Lake Colville at 10 or 11 meters lower. Lake Colville drains away at the surface to the Mackenzie River like a regular lake. Lac Belleau drains into a sink, a boulder clogged sinkhole here, and then comes up a springs, a straight line distance of 20 kilometers. It hasn't been ditraced yet. Fall height of 75 meters, so the good hydraulic gradient, steep for Karst. The slide can't show you the legend of Neodalin. The local Indian population, Cree Indian, well understood that the lake drained underground. They had a small village up here, and the story is of two young chieftains who got bored with the local ladies and took off down the lake to meet the ladies of in the fresh pots of the larger villages on the Mackenzie River. They disappeared into this sinkhole. They passed through the innards of a salmon, a giant salmon, through the innards of a giant trout, and then they flew out in their canoes into a spring here. That's much more exciting than the ordinary karst geomorphology. And they're quite right, that is the drainage that we see. Next, please. This is Lake Tunago. I showed you, you can see the giant flood wash, the Jokkelaub or scabland washing here. You'll see that all the ponds show signs of having higher water, including Lake Tunago itself. It doesn't quite fit on the screen, about 100 square kilometers in area. Whoops. It doesn't quite fit on the screen to tell you that according to some seismic exploration was done for oil and gas up here 30 years ago, and a local engineer who worked on it told me that the seismographic data were very poor because of around here the line was badly shaken by the rumble of water sinking into the karst. It's sinking into one of these hydration ridges that is poorly denominated coming down there. I've seen it only, I've never set foot on this bit, I've seen it only from a helicopter. Last picture, please. That's this is Bear Rock itself on the Mackenzie River. This is the drainage from Great Bear Lake coming into it, about to mix. This is this giant dolomitic anhydrite gypsum solution breccia with another thousands of square kilometers of karst development on it, but I'll tell you about that in another story. Thank you. Finish.
Okay, thank you. Any questions? Okay. Well, if you're too shy to ask a question in person, you can always type it in the chat.
Just put it in the chat.
Yes. Okay, so our next speaker is Alan Fryar, and he is a professor of Earth and Environmental Sciences at the University of Kentucky, and he's conducted research and technical outreach projects in China, India, Indonesia, Morocco, Pakistan, Thailand, Turkey, and the US, all over the place. So take it away. Let me give you your title too. So you are variable responses of mountainous karst springs to seasonal precipitation.
All right, thank you, Pat. Here we go. Can everybody hear me and see me?
Yes.
Thank you. I'd like to acknowledge my co-authors, Josh Barna and Brett Howell, former master's advisees. Their thesis research underpinned a lot of this presentation. So, as many of you no doubt know, springs respond to precipitation as a result of different controlling factors that include climate, lithology, geologic structure, relief, and land use, land cover. And as we've seen, infiltration mechanisms can be both diffuse through soil and focused through sinkholes and other depressions. And this infiltrating water displaces water from the pore space already resident, as well as water in fractures and conduits. And as a result, water temperature and chemistry at springs can vary over timescales ranging from event hours to days to seasonal or even longer to annual timescales. So the objective of this talk is to highlight the range of responses for two different springs and address what we may be able to infer about hydrologic behavior from these spring responses, and in particular, how the controlling factors that I mentioned in the previous slide interact to regulate flow path connectivity and responses to external forcings, such as climate and land use, land cover, and implications thereby for understanding the susceptibility of spring flows to environmental changes. So my case studies are from temperate mountainous regions with seasonal precipitation, the Middle Atlas Plateau of Morocco, which has a Mediterranean climate, and the Gheorghe province, Southeast Asian karst in China, which has a monsoonal climate. So study area 1, at left is a map of Morocco, at right is a Google Earth image, and I'm going to focus on 3 springs, Riba, Zaruka, and Sidi Rashid. Zaruka is the water supply for Afrin, town on the plateau, Sidi Rashid for a neighboring town, Azru, and Riba is one of the major water supplies for the city of Meknes. And you'll note subsequently this north-south cross-section. So the Middle Atlas Plateau consists of tabular Jurassic carbonates overlain by thin rocky soils. And the development of preferential flow paths and of karst have been promoted by faulting, but also limited by dolomitic lithology. Recharge is associated mainly with cool season rainfall between October and April on the plateau, averaging about 1 meter per year. Land use, land cover are mixed, including rangeland, forest, and the towns that I mentioned, and there's been land degradation by deforestation and overgrazing. And this is the cross-section I alluded to, south to north, and we're going to focus on the upper right on the plateau and at the foot of the plateau. And the lithology here is liassic, calcareous dolomites, and dolomitic limestones. This is a view from the Middle Atlas Plateau near Afrin in July of 2014. And this is a photograph of one of the spring orifices in the spring complex at Riba at the foot of the plateau. And this is a main orifice covered by a spring house water supply for Meknes again, and you can see water flowing past this head gate. This is February 2014. And this is what it looks like later in the dry season. This is September 2014, and all the water is either being piped to Meknes or flowing underground. Our methods in terms of field monitoring included acquisition of weather data from the National Weather Authority. They're stationed at a FREN, air temperature, precipitation, and barometric pressure at hourly intervals. We monitored water temperature and stage at hourly intervals at Sidi Rashid and Zaruka Springs on the plateau, and water temperature at hourly intervals at Riba at the base of the plateau, and also had daily samples collected each morning at Zaruka on the plateau for oxygen 18 and deuterium, and all of this was between March 2014 and May 2015. So the first graph here shows spring temperature. Sidi Rashid and Zaruka are shown on the left-hand y-axis, Riba on the right-hand y-axis, and you can see here that Zaruka is relatively flat line. Sidi Rashid shows some sinuosity with a bit of noise, and Riba is kind of a hybrid. It's very gently fluctuating but relatively flat up until November, when it starts to become much more erratic. At Zaruka, temperatures were stable within less than 1/10 of a degree Celsius plus or minus. At Sidi Rashid, we saw a time-lagged seasonal signal relative to air temperature, with the water temperature minima in May, June, and maxima in October, and responses to individual storms superimposed on the signal. At Riba, we saw differing seasonal responses with relatively uniform temperatures from April to November, and then relatively flashy from November to May. This is a plot of stage for Sidi Rashid and Zaruka, shown on the left-hand y-axis, and precipitation on the right-hand y-axis. And what you can see is sort of a sinusoidal response, again, for both springs. Note that there is a greater amplitude for Sidi Rashid, about 4/10 of a meter, than there is for Zaruka. And this is a plot of oxygen 18 on the left-hand y-axis and deuterium on the right-hand y-axis. This is a 10-day moving average to smooth the noise. And what you can see here is that the signals for the two isotopes, O18 in brown, deuterium in gray, are moving in and out of phase for much of the year. So to summarize, for stage and stable isotopes, the stage at Zaruka and Sidi Rashid track together with a broad minimum in late summer. These are vacation towns. We think it's attributable to municipal pumping, and muted responses to individual storms superposed on the signals. Water temperature at Sidi Rashid tracked the stage from March to October, but then declined relative to stage, and the O18 and deuterium signals diverged except from March into April. We interpret this as meaning that Zaruka and Sidi Rashid water temperature signals indicate relatively efficient thermal exchange with the matrix, that is, flow is not conduit dominated, and that Riba appears to be fed by multiple flow systems, with the flow system from the plateau dominating during the dry season, and a local flow system that's significant during the wet season. And the divergent deuterium and O18 signals at Zaruka indicate changes in sources of recharge, going from less to more evaporated as you go from wet to dry seasons. Our second study area, Guizhou Province, China, is shown in the national map outlined at upper right and then at lower left. The gray represents carbonate outcrops in the Chinese portion of the South Asian karst, and the red star is our study basin, which is the Hozhai Basin. It's about a 74 square kilometer spring shed. It's been extensively studied for over 2 decades. Consists of cockpit karst developed in faulted Triassic carbonates mantled by clay soils. And the southern part of the basin is marked by a well-developed and relatively well-delineated conduit network with multiple branches. There are rains during monsoon season from May to October, totaling about 1.3 meters per year. These fill the conduit network and can activate overflow passages. Land use, land cover is mixed. Like in Morocco, there's agriculture, but in this instance, it's intensive cropping, some forest, towns, as well as quarrying and industry, and like Morocco, deforestation has degraded the landscape. This is a digital elevation model, 10 basin map. Note that elevation is highest in the east and southeast. Flow is toward the northwest to the outlet marked by the red star. The dashed blue lines represent the inferred conduit network, which is integrated with a surface stream and intermittent network marked by the solid blue lines. This is classic sort of peak cluster, South Chinese landscape, and you can see in the foreground rice paddy. And this is the outlet spring, Maushuakung. And note that there is instrumentation here, but we installed our instruments at an instrument shelter several hundred meters downstream along the spring run. So our methods in terms of field monitoring included monitoring rainfall at 5-minute intervals about 8 kilometers southeast of the outlet, electrical conductivity and stage at 5-minute intervals, as I said, about 370 meters downstream of the outlet. And we sampled for field parameters, water temperature, electrical conductivity, and pH, as well as solutes, which I won't get into detail here about, as well as stable isotopes at hourly intervals for 46 hours at the outlet. And this followed 60 millimeters of rainfall in about a 53-hour period. This was all between June 21st and June 25th of 2018. So this diagram here shows electrical conductivity on the left-hand y-axis and water level and precipitation on the right-hand axis. And you'll note the lower plot here is the hydrograph, the medium gray becoming lighter past the peak discharge at the point where we started to monitor or started to sample at the outlet. And then above it is the plot of electrical conductivity, and then again becoming a lighter gray when our sampling began. This is our manual measurement of water temperature and pH at the basin outlet spring, temperature in the black dots on the left-hand y-axis, pH on the right-hand y-axis, and the gray triangles. And you can see 2 declines separated by a recovery in between. Water isotopes, you actually see 3 declines. Deuterium, left-hand y-axis, black dots, oxygen 18, gray triangles on the right-hand axis. So decline, rebound, decline, rebound, decline, rebound. So the minima in water temperature, electrical conductivity, pH, and also solute concentrations about a day after the stage peak indicate the arrival of storm flow at the outlet. The rebound in the secondary minima suggests arrival of the second storm pulse at the spring, which we think represents fast and slow flow contributions from different parts of the conduit network. We think the 3 drops and rebounds we see with the water isotopes may indicate recharge pulses from progressively farther up the basin. As you go higher in elevation, you get more depleted isotopic signals. This is just the basin map again, showing the inferred conduit storm flow paths through the basin. And I want to focus on this karst window. Again, our outlet is here. This is almost exactly a year before our monitoring, a previous trip, and you can see the karst window flooded. And 5 days later, the water level had dropped about 5 meters, and it's still 2 to 3 meters perhaps above the conduit. So to summarize, in terms of the contrasting responses, in Morocco, we saw occasional subtle responses to storms with relatively diffuse, dominantly cool season recharge, slow, matrix-dominated drainage and refilling, and limited karstification of dolomitic limestone. Whereas in China, we saw a flashier response with shorter time lags, reflecting more intense rainfall and focused recharge during the monsoon, more rapid filling and drainage of sinkholes and karst windows, and more pronounced conduit development attributable to greater chemical weathering and more soluble carbonates. And I'd like to leave it there with the acknowledgements. Thank you.
Thank you. Wow, that was great. Good, short, to the point. We have time for questions if anybody has any questions.
And if not, that's okay too, and I can stop sharing and we can get back on schedule.
Okay. Thank you very much, Alan. Our next...
Sarah, we're close by. You can catch me later, or I'd be happy to answer your question, whichever you prefer.
Okay. Okay. So our next speaker is Brian Chamba. Do I have that correct? Let's see if I'm right on my schedule here. Yes, Brian Chamba. And Brian is a geology student in the School of Earth Sciences, Energy and Environment in Ecuador. And he's going to talk about the first electrical resistivity tomography study applied to an Ecuadorian cave, insights into the Amazon karst. So, Brian?
Hello, everybody. Thanks for the presentation. Just to update my information, from Monday, I am a graduate student of Montana Tech. And first of all, I want to express my thankful to the opportunity to share my research in this high relevance workshop. And about my research, it's important to say that cavity detection is one of the main challenges related problems in the Amazon region, and for the reason I'm presenting the first electrical resistivity tomography study applied to Ecuadorian cave. This work was done by me, Brian Antonio Chamba Vasquez, and by my advisor, Elisa Joana Pispa. So it is the outline. First, we will have the introduction where we will cover the study area, cave features. Then we will have the problem statement, the objective, the method that is the clue part of this presentation, that is the electrical resistivity tomography. Then we have results that are the inversions, the discussion, and the conclusion. So the chapter number 1, introduction. So about the study area. Tena is a small city located in Ecuador. Ecuador is a small country located in South America. Furthermore, Ecuador is located in the equatorial latitude. And about the geology, Tena city is located in the Oriente Basin. Oriente Basin basically is the Ecuadorian part of the Amazon Basin. Furthermore, our cave is located, Uctuijichanga cave is located 5 minutes northward to Tena. About the geology, the Uctuijichanga cave is located in the Napo Formation. Napo Formation is 100.5 to 93.9 million years in age, and Napo Formation consists in an intercalation of sandstone conglomerates and limestone that corresponds to a shallow marine environment that corresponds to a marine platform. About the cave features, the Uctuijichanga cave is situated at 510 meters above sea level, and it is 1,174 meters in length. About the cave feature, we have defined 2 main rooms. First, we have the cave entrance that is approximately 1.9 meters in height and is approximately 3.2 meters in width. About the cave windows, it is a little bigger with a height of approximately 2.5 to 3 meters with a width of approximately 3 to 5 meters. Problem statement. Here in this picture, we could see previous map of the Uctuijichanga cave, and it's really interesting to analyze how is the resolution, the scales, and the feature of this map. It is a really huge problem in Ecuador because almost all the almost all the Karst caves located in the Amazon region has this kind of maps. For this reason, it's really important to start to create solutions to solve this urgent necessity. In order to solve this necessity, we have developed a cheap geophysical equipment that will allow us to characterize the Amazon Karst system in high scales. So the objectives of this research was, first, to demonstrate that the sustainability of the electrical resistivity tomography technique through geode inversion for characterization of shallow caves. Second, to evaluate the reliability of the electrical resistivity tomography in detecting no shallow cavities in the Amazon region. And finally, to identify and characterize different geomorphological features underground. To do it, we use an electrical resistivity. So basically, resistivity is a measurement of how much a material opposes electricity. So using this idea, we created this inexpensive resistivity equipment that basically is composed for those parts. First, we have a battery that is the power of source. Then we have this converter to convert DC to AC current. Then this converter is connected to these electrodes that are called current electrodes. And then electrodes create an electrode file. And this electrode file is measured for this multimeter that measures the current. Then separately, we have these potential electrodes that measure the potential created by this electrode file. So in the file, we have 2 measurements. First, the current and the voltage. So with this information and using this equation, first, the alternative form of the Ohm's law, that is electrical field is equal to resistivity times current density, and then using a mathematical derivation, we could create this equation. That is apparent resistivity. So apparent resistivity is equal to the voltage over the current times a geometric factor. So about the geometric factor is different according to the arrangements of the electrodes. Basically, arrangement means how we could sort this electrode. For example, we could put this potential electrode in the middle part and this C2 electrode at the end of the line, and it will be another profiles. But in this study, we use a dipole arrangement because it's the most sustainable arrangement in order to reach our objectives. Here in this picture, we see the dipole arrangement and how it works. So basically, we have the electrical currents, the electrical electrodes, the current electrodes in the first part. Then we have the potential electrodes. This current electrode has a distance called 8, and this potential electrode has the same distance. From the middle part to the middle part of the potential electrode, we have a distance called L. And when we have to take a measurement, we should maintain this current electrode stable while we move this potential electrode. And we capture the first measurement. Then if we have another measurement, we move the potential electrode and we catch another measurement. And we could do it until reach our theoretical depth, but it's important to say that if we reach higher penetration depth, we'll lose resolution. For this reason, it's important to play with the resolution and with the depth. So the results. So in general, we developed 13 profiles, and these profiles were done in the initial part of the cave. Why? Because in this initial part, we have two projections of the caves on the surface, the cave entrance and the windows of the cave. So in this part, we could test the method. Here we have the profile number 1. It is an electrical resistivity profile. So how we could interpret these profiles? In this part, we have depth, and here we have the distance of the profile, and here we have the values of resistivity. Blue colors means low values of resistivity, while dark colors, red colors, means high values of resistivity. So the high contrast between air-filled voids and conductive layers create these resistivity anomalies. And when we see a resistivity anomaly on the profile, we could say that it could give us a signal of the cave. In that case, in profile Y1, we was not able to reach the cave entrance because this profile was really short. For the reason, we create the profile number 2, and in this profile, we could detect the cave. But it's really interesting to analyze the profile number 1 and 2 together because we could see that these profiles match with the interpretation, because first here we have a conductive layer that corresponds to the limestone. Then we have a less conductive layer that corresponds to the marlstone layer. And finally, we have another intercalation of the limestone layer. And obviously, here we have the resistivity anomaly. And here we have another resistivity anomaly, the same resistivity anomaly. Also, it's important to say that in this part, we have an unknown cavity that because here we have another resistivity anomaly. And here we have another resistivity anomaly, but this resistivity anomaly corresponds to holes and joints. Here we have the profile number 3 and 6, and the profile number 3 was done over the window, a cave window, and here it's really interesting to see that the windows of the cave match very well with the resistivity anomaly, as you could see. But also it's important to say that at the first instance, we thought that the electrical resistivity tomography method will be able to give us an idea about the geometry of the cave. But as you could see, the geometry of the cave and the resistivity anomaly does not match, but the position of the cave match with the resistivity imagined. Here in profile number 6, that was done in a park where we don't know the projection of the cave exactly, here we have this profile. And here we could see clearly a signal of the cave. And it is a way to say that the method is working. Discussion. So first of all, we have defined 3 geological units according to their resistivity range. So first we have a limestone layer that has a value from 0 to 50 ohms. Then we have a marlstone layer that has resistivity values from 51 to 18 ohms. Then we have the superficial karstic cave that has a resistivity value from 81 to 100 ohms. And then we have deeper karstic cave that has resistivity values from higher than 100 ohms. And what is important to say this? It is important because according to the literature, resistivities could vary a lot according to the geological unit, but in our research, we have defined really a specific range of resistivity for each geological unit. It is because in Ecuador, due to the equatorial position, we don't have really high change in the climate, because here we only have 2 seasons, the dry season and the wet season. And for this reason, we don't present really high change in the resistivity according to the geological unit. And how we could prove that our method is working? We could prove that our method is working because we did repeated profiles. This profile was done in the same position, and this profile was done in the same position, but in a different date. But as you could see, the behavior of the resistivity is almost the same. We have the conductive part, and then we have the anomaly. And also we could see that we have another unit that match very well. And with this, we could say that there is no noise that is creating about the electrical resistivity profile. Conclusions. So our conclusions first are, first, this study demonstrated that the modifier dipolarized was the best fit for our given task because it increased the theoretical depth of the profile without a significant increase in noise. Second, the electrical resistivity tomography method proved to be very useful in detecting the location of the shallow cavities at the Uktuihichanga cave, but it could not display a precise geometry of the cave. And finally, the electrical resistivity tomography appropriately differentiates 3 units, and it showed the occurrence of possible unknown caves and cavities and possible faults. So it was all. If you have one question, please let me know.
Questions? I have a question, Brian. Okay. So you were looking to see if you could determine the morphology of the passage using that method, and you determined that you could confirm that there was a void there, but you couldn't really determine the morphology of the void. What do you think it would take? Do you think it's a matter of resolution of your signal, or what do you think it would take, or is it possible to actually determine the morphology of a cave using that kind of method?
For example, in this profile, we at the first instance we tried to determine the geomorphology of the cave, but with the pass of the time we demonstrate that there is not a exact relationship between the geometry and the resistivity anomaly, but I think that using another arrangement, we will be able to maybe demonstrate that this method could define a geomorphological study. But we should do different arrangements do different kind of inversions, and we could prove that.
Okay. Okay, thank you. Any other questions? All right. If you do have questions, as we keep saying, you can put them in the chat and we can direct them to the presenters. So our next speaker, or maybe we have two speakers, or maybe one, is Lindsey. Lindsey, how do you pronounce your last name?
It's Rasnake, but I was thinking there was one more before us, Chloe, I think.
Yeah, I think it's me.
Right, I totally skipped over you. Chloe, no wonder you look like you're freaked out. She's like, oh my God, she's not coming. All right, my apologies to Chloe. You are next, and Chloe is a PhD candidate in the Department of Hydrology and Atmospheric Sciences at the University of Arizona in Tucson. Is it a little hot there?
And, it's very hot.
And she also leads multi-day science and research trips for high school students at the Mount Lemmon Sky Center. You're probably not doing that anytime soon right now, right?
No. Our entire mountain burned in a wildfire this summer, so
oh my God,
not for a long time.
So Chloe's talk is Representing Uncertainty with Diverse Model Ensembles, a Test Case in an Alpine Karst System. So Chloe, you're on.
Okay. All right, can everybody see my screen?
Yes.
Yes, okay, great. So I'm gonna give a short version of this talk, and if you would like the full version, the video link should be on the Karst 2020 website, and I can also share it in the chat, because this is a work in progress, and I would really, really like questions and feedback and criticisms from you all. So what I'm trying to do is model karst systems, which is hard. And I'm using an ensemble modeling approach, so many, many different models of the same site, to try to understand the uncertainty in the model predictions. And this project is a collaboration with myself and Fryar here in Arizona, and then Zhao Chen and Nico Goldscheider at Karlsruhe Institute of Technology in Germany, which is where the field site that we're using is. So, as you all know, a major challenge in karst systems is that we often don't know where the conduit networks are. So this is a hypothetical example. And one of our first major goals was just to come up with a system that can automatically generate many, many different plausible conduit networks for a given site, constrained by the local geology, right? So you could have simple connections, more complex connections, many different options, but using pretty minimal data. So we wanted to start with just the bare bones and then see how that worked, and then add in data gradually as we went to try to figure out what the minimum necessary data would be. And then once we have that ensemble of multiple different networks that could exist in a given system, we wanted to identify what specific data is the most useful to add, so that we can prioritize field data collection efforts and resources. And then use that ensemble of multiple different structures to compare the impact of structural uncertainty and parameter uncertainty on the model predictions. So historically with groundwater modeling, we've really focused on parameter uncertainty, but in karst especially, the uncertainty due to the shape and arrangement of the conduit network structure is really important, and is likely more important than the uncertainty due to the specific values of parameters that we assign. So in this case, parameters are things like the conduit roughness, the tortuosity, the conduit matrix exchange rate, that type of thing, where it's not necessarily something you can go out and map. So what we found so far, and again, this is a work in progress, this is a subset of 10 networks that were automatically generated for our field site. Can you see the mouse on here? Yeah, okay. So the springs for the system are over here, so that's consistent in all of these. but then the network that drains to the springs is different in all of these automated ones. And we tried to get a range of, you know, branching and different connection patterns that could all exist given the geologic setting. But our first finding is that if you look at the true network, so this is what we know the network looks like based on mapping and tracer tests. None of the networks that we generated look like the true network, which means that our process for generating this ensemble isn't doing a good enough job of sampling the range of possibilities. So what I'm currently working on is revamping that whole network generation process to do a better job. But even given that, we found some really interesting stuff. The first of which is that if you look at the background color on all of these, that's indicating the fit from the predicted spring discharge to the observed spring discharge. Poor fit is dark, good fit is light. And what I think is really interesting is that all of these networks, if you take, we randomly assigned multiple different parameter sets to each network and then picked the best of those parameter sets, best performing parameter sets. So this is for the best parameter set, how well it fit the data, and they all did a fairly decent job. So if you were to try to identify which network was closest to the true network just based on the fit of the predicted spring discharge to the observed spring discharge, you would not be able to tell. So spring discharge isn't really allowing us to discriminate between structures, which means that we need a different type of data or perhaps a different way of analyzing that data to be able to tell apart which networks are plausible and which ones aren't. And then the other thing that we looked at with this ensemble is the importance of parameters versus structures. So again, these are 10 different network structures, and for each one, we have many different parameter sets that were really randomly assigned. We did not do extensive parameter calibration. But what we did then is look at the difference between spring discharge predictions across different parameter sets on the same network and then across different networks. So this is just an example for two networks, these two here. And you can see there's 10 different blue lines. That's for this network, 10 different parameter sets on that network, and 10 different green lines. So that's 10 different parameter sets on this network. And what jumps out here is that the distance between the difference in predicted spring discharge patterns within the same network is much, much smaller than the distance between predicted spring discharge across two different networks. So what that tells us is that the network really matters a lot more than the parameters. And again, because historically modeling efforts have dedicated most of the computational resources to parameter estimation and understanding parameter-based uncertainty, this result really tells us that understanding the structure and the uncertainties associated with structure are possibly more important, and that it's worth devoting time and resources to exploring multiple different structures as well as multiple different parameters. Okay, so that was a really quick overview, but I would really love your comments and feedback, and you can get in touch with me via email afterwards if you want me to email you the full 15-minute talk with more details. So yeah, questions, please. And I don't know if Autumn, you want to moderate the questions or anything, but or you can just ask directly.
I have a question.
Yeah, please.
When you were talking about structure, did you mean like geologic structure? Is that specifically what you were talking about?
Yeah, good question. So in this case, we have one single geologic structure, and we have many different conduit network structures within that geology. So in this case, I'm just looking at the conduit network structure. I'm not looking at multiple different geologic structures. Ideally, in the future, I do think it would be really interesting because there can be different interpretations based on the same geologic map of what the underlying structure is, to start with the same geologic mapped data and consider 2 or 3 different interpretations of what the geology might be, and then for each of those different geologic interpretations have multiple conduit networks. But at this stage, it's just the network structure.
So when you say network, I'm sorry, I'm like being...
Yeah, no, this is great.
Network structure, you're talking about the morphology of your conduit?
Yeah.
Okay.
For this hypothetical system here,
mm-hmm.
Do the networks look like the yellow ones, or do they look like the blue ones, or do they look like the green ones?
Okay.
Like what areas are connected to what other areas? What's the length of the network? How much branching is there? That kind of thing.
Okay, thank you.
Mm-hmm. Yeah, good questions.
Hi, Chloe. This is Alan Fryar. Can you hear me okay?
Yeah.
I put 2 questions on the chat, and Pat may have asked the first one, but I was so busy typing, I may have missed it. How geometrically or architecturally was your model parameterized? And second, there's been a fair amount of work done in recent years on using additional information besides discharge, such as electrical conductivity or temperature, to parameterize or to constrain models.
Mm-hmm.
Have you thought about those?
Yes, I actually was really interested to see in your talk the spring temperature time series,
mm-hmm.
because that's something. So the idea here with this is like the first part of this project, and the idea was to say what's, bare bones absolute minimum data, and then based on the results that we got, what data do we need to add? And I think looking at temperature time series would be really helpful. The other thing we're considering is tracer tests. We have a lot of tracer test data for this site that I've just set aside and not looked at yet. But I'd like to model the, tracer concentration time series and compare that to the observed tracer results and see if that can help us constrain a little bit more. So yeah, absolutely. I want to add in more data types.
I will say in my presentation, we did time series analysis for the sake of brevity, a little bit like you. I just didn't include any of that. But clearly there's a robust literature out there on it.
That's good to know. Yeah. The one other limit right now is that we're using the stormwater management model to predict the flow, and it's limited in its ability to model temperature or like contaminants and tracers. So we're thinking about switching to a different model to use for this. Maybe ModFlow CFP, if that can perform better. But yeah, great questions. Thank you.
Any more questions?
Particularly if you have
more, but I'm gonna let other people.
Yeah, no, if you have criticisms, this is still a project in its early stages, and so I would love to hear critiques now before I get too far.
Okay. Does anybody else have any questions or critiques for Chloe? Very cool study.
Thank you.
If not, I guess Lindsey is up.
Great, thank you.
Thank you very much. And Lindsey is a graduate research assistant with the Indiana Geological and Water Survey. And it says you've got all these MPA/MSES candidate in the O'Neill School of Public and Environmental Affairs at Indiana University. And Lindsey's going to talk about characterizing perennial bedrock springs in the low-yield aquifer region of southwest central Indiana. All right. Well.
Yeah. Thank you. I'm Lindsey. I'm also going to be presenting with Stephanie Laguerre as well. And so she is also a graduate assistant working on this project. And so I'll let her talk here in just a second, but yeah, we're going to be kind of talking about some of the initial results we've had. We're still in the early stages of this project through the Indiana Geological and Water Survey on these groundwater springs in the southwest central region of Indiana, which we'll kind of start to refer to as SWCI. So just so no one gets confused, but I'll let Steph maybe do a quick introduction and then start us off.
Hi, I'm Steph. So we will go into the groundwater in the rural southwest central region of Indiana has been used for a variety of purposes. This includes drinking water, agriculture, livestock, and commercial use. All of these factors make them important features for the communities in the region. The karst springs have been important areas for the community to gather as the land is riddled with caves and sinkholes but otherwise lacks surface water. On the other hand, mineral springs became the cornerstone of the spa industry within the region during the early 1900s. These springs have previously been evaluated based on rock and aquifer type, flow, and biogeochemical characteristics. However, there's a gap in the understanding of the spatial relationship between these springs, as well as the changes in spring quality over time. Next slide, please. To fill in this gap in understanding, the Indiana Geological and Water Survey is partnering with the Center for Rural Engagement on this project, investigating a subset of the 360 known springs in 11 counties in the southwest central Indiana region. The project goals are to establish baseline water quality and quantity conditions in the SWCI region and compare those to historical data. To examine water-rock interaction pathways in their relationship to spring quality, and to foster community engagement through a publicly accessible online geospatial database and provide education to stakeholders. The goals are imperative to better understand the spatial distribution and quality of water in the region, as it's still a limiting factor to the economy and human development. Where contemporary analyses can be compared to historical results, the goal is to also illuminate the impact of anthropogenic activity or climate change as well. One example of comparing historical to present data is Pluto Springs in French Lick, Indiana. The pictures are shown on the bottom of this slide. This mineral spring is one example of one that was important to the economy of the region because tourists would come to drink the sulfur mineral water for its medicinal properties. The left picture shows the spring in the early 1900s, and the right is us during our 2019 sampling season. Next slide.
So as the title of the presentation suggests, we're characterizing these springs in several different ways. One of the ways we're characterizing that we're going to particularly focus on in this presentation lies at the spatial scale. So the SWCI region can be split up into several different physiographic provinces based on their underlying geology and biogeochemical properties, stuff like that. The two provinces we've investigated at this point in the project are the Mitchell Plateau and the Crawford Uplands. The Mitchell Plateau is a sinkhole plain which is made up primarily of limestone, while the Crawford Upland generally has a more diverse lithology, so it also contains clastic layers like sandstone and shale. And we're also delineating springs by order according to their discharge rates, identifying them as cave, karst, mineral, or otherwise. And we also expect that the water-rock interaction type will be identifiable through the water chemistries, and that will be supported by our sulfur and carbon isotope analysis. So in our first field season last fall, we were able to sample 33 spring sites in 3 counties. 10 of those were in the Mitchell Plateau, which you can see is the light blue region on this map, and 23 of those were in the Crawford Upland, which is the purple region. So we collected kind of a general suite of water quality and quantity field data, and also conducted some lab analyses kind of to ascertain those baseline water quality conditions of the springs. Unfortunately, due to a mix-up with the E. coli testing kits, we were only able to determine a qualitative presence of E. coli and not a quantitative value, but In this field season, we will be returning to those springs with the correct testing kits, so we'll be able to kind of obtain that quantitative value of bacteria in those.
So from the 33 sites we acquired during our 2019 sampling season, we were able to determine some preliminary results. Our data analysis split the karst springs into two primary clusters. These were predominantly separated by county, as you can see on the map on the left. The yellow dots are in Monroe County, and that's cluster 1, and the red dots are predominantly in Greene County, and that's cluster 2. This suggested that the physiographic provinces influenced the spring chemistry. For instance, nearly all sites with elevated sulfate levels occurred in the Crawford uplands, as we'll go more in detail with in a few slides. This was likely due to a more diverse lithology, particularly with regards to sulfate minerals within the Crawford uplands. The figure on the upper right shows that we saw more variation in the chemistry of the springs in the Crawford uplands compared to those in the Mitchell Plateau. In comparison, the figure on the bottom right also includes how the outliers in the Crawford uplands would be more likely to cluster into their own groups. This informs that the two primary cluster groups group as they do, not because of differing types of dissolved solids, but rather by the amount of dissolved solids, as we'll expand upon in the next slide. Next slide, please. So this map shows the conductivity, and the size of the circles goes with the how conductive the spring water was. This shows that there's a general relationship between conductivity and older bedrock units. Excluding mineral springs that are towards the bottom of the graph in Orange County, conductivity was higher close to and in the Mitchell Plateau, which is made up of older bedrock units as compared to the Crawford uplands in Greene County, as Lindsey will go more in depth with in a few slides. Next, the figure on the top right shows the relationship between the measured conductivity and the calculated ionic strength. There's a positive correlation as expected. Moreover, it shows that there is a greater conductivity for the springs in cluster 1, which on the map are the yellow circles, and in this figure are the pink diamonds, as compared to cluster 2. This shows that cluster 1 is differentiated from cluster 2 by the elevated amount of dissolved solids. The size of the symbols on this graph also is indicative of the discharge, so that shows that while not definitive, there does seem to be some grouping within the clusters that goes with the discharge. The figure on the bottom, however, demonstrates again how cluster 1 has greater dissolved solids than cluster 2 by comparing dissolved calcium to conductivity. Next slide. So this map now shows the sulfate. Again, the larger circles are for higher sulfate concentrations, while the smaller circles are for lower. We'll note that the two springs with the highest concentrations are located in Orange County, and they are known mineral or sulfur mineral springs, so this fits what we expect to see. These springs had a high enough sulfate concentration to form their own clusters in our data analysis. Outside of those sulfur mineral springs, the highest sulfate concentration was in a spring, which you can see pictured here, located in Greene County. It had iron staining at the discharge point, as well as elevated iron and manganese levels. Sulfate indicates water and mineral interactions with more than just carbonate minerals. So sulfates are considered the primary source in limestone karst settings, while sulfate or oxidized sulfide mineral could be the source where clastics such as sandstone and shale are encountered. This is what we expect to see with the Crawford uplands again, because of the more diverse lithology of the physiographic region. In the future, we will use sulfur isotopes to support this interpretation. Heavier ones should show that we have sulfate, while lighter will show sulfide origin. However, due to time and resources, we'll only be sampling ones that are at or above 100 milligrams per liter of sulfate. And due to our current subset, we don't have enough to provide detailed analysis. Next slide.
So we're also using spatial analyses to tease out the potential factors which could be influencing the differences in chemistry, which is causing these clusterings. One possible factor is the stratigraphic region in which the springs fall, which we've sort of talked about a little bit. Maps here are showing the aquifer systems of Monroe County on the left and Greene County on the right. The groups are in order by age, with Raccoon Creek in the light blue being the youngest, and the Borden group being the oldest, though we didn't sample any in the Borden region this go around. The Raccoon Creek group of Pennsylvanian age is mostly comprised of sandstone and shales with limited amounts of limestone. It's also typically a fairly limited groundwater resource, so more sites collected from this region will hopefully help form a clearer picture of the aquifer capacity and its influence on spring chemistry. The Stephensport and West Baden groups fall under the same aquifer system of Mississippian age, and those are greatly composed of limestone and just some sandstone with minor amounts of shale. And these groups are also more heavily characterized by karstic conditions. And then last, the Blue River and Sanders groups are comprised of primarily limestone, and so are also heavily characterized by karstic conditions as a result. So as we sample more sites in more counties, we're really hoping to perform some more in-depth spatial analyses as to the role the bedrock aquifer plays in spring chemistry. So we're hoping to get some more detailed results after our upcoming fall sampling season. So we're also looking at elevation and the role that it might play in spring chemistry. So here in the map on the right, the spring clusters are shown with elevation from low in the green areas to high in the brown areas. And we can see that there does seem to be some correlation between the low elevation with the second cluster in red and the higher elevation with the first cluster in yellow. I've also added this map on the left just to orient everyone to where the sites are, particularly paying attention to the counties. And one interesting thing to note are these two springs in the northern portion of Greene County. They actually fall at about the same elevation but fit different groups chemically. As you can see, they're in two different clusters. And so we think that this could potentially be due to difference in the bedrock aquifer, which we talked a little bit about on the previous slide, or it could be residence time in the aquifer, which can be a function of either a larger aquifer feeding the higher conductivity spring, or possibly tighter permeability or smaller fractures causing that higher conductivity spring to have stayed in the aquifer longer, which allows for more of the water-rock interaction and mineral dissolution. Or it could be none or a combination of all of these. So hopefully with, like I said, more spring sites, we'll be able to tease out some more of these factors. So finally, a major deliverable of this project is our online geospatial database, which will house all of the data that we've collected, as well as any data we have from historical studies. And if it's okay, I'm actually going to switch over to this web page. So you guys just let me know when you can see the web page.
Looks like we can see it.
Awesome. Okay, so this is just a demo site. It's definitely not up and running yet, but this is just starting to kind of show how we're going to allow people to use this tool. So you can see here all of our spring sites, and users will be able to interact with this data and also add their own. So I'm just going to click on one of our publicly accessible springs. So after looking at an individual spring, they'll be able to see the full suite of data that we've collected, and also look at images, and they can add their own data with approval from us. And we're really just hoping that this is going to increase the understanding and awareness of these springs and the important groundwater resources, and also kind of foster some community engagement, which is one of the main goals of our project, as we stated. And then just some provisional conclusions we can make from the data that we have so far is that greater variation that we talked about in chemistry in the Crawford Upland Springs, which is attributed to the more diverse lithology of the region. And additional samples from this season will expand the number of springs in both provinces and in other provinces, which will enable a better evaluation of the chemical differences and what role the province might play in influencing spring chemistry. And we'll also be able to use those samples to determine estimated low flow discharges, which will be compared to chemical character and mineral saturation indices to ascertain diversity of minerals interacting with the groundwater aquifers. And then additionally, as I stated, we'll be revisiting the springs we sampled last year. So hopefully we'll get a better understanding of the bacteria in those springs. So that's all we have. We'd love to take questions if anyone has any.
I guess I'll ask one.
Okay.
So I assume that temperature is also one of the parameters that you measured, and if it is there any differences in temperature, water temperature in all of those springs, or are they pretty consistent throughout?
We did look at temperature, yes. I don't know that there is any significant difference that we could tease out thus far. Steph, you might have some more insight on that.
Not that I recall more than maybe seeing an influence as we were sampling later in the season.
Okay.
Yeah, water was definitely colder as we went on. We sampled into November, so.
Okay. Does the water chemistry change much also, like seasonally? I mean, I guess it would, or does it?
Yeah,
it does.
Oh, sorry, go ahead, Steph.
No, you can take it away.
I was just going to say that's part of the reason why we're sampling in low flow conditions, which means we have a really tight sampling window. And that's one of the reasons why we were only able to hit 33 sites last year, is that we do think that it probably changes throughout the season, and we wanted to get those baseline low flow conditions as kind of a jumping off point for what might be influencing the spring chemistry.
Okay, thank you.
Yeah, or Steph, if you have any more to add, I'm sure you have a better understanding than I do. Neither of us are geologists by trade, so bear with us.
No, that sounded good to me.
Yeah.
Well, I think it's great that you're making your data web available. That's awesome.
Yeah, that's, I think, one of the most exciting things about this project is how it's not only focused on, you know, the research itself, but also making it available to people and using it to interact with people who maybe didn't have any idea what role groundwater plays in southern Indiana. And so I think we're excited to see where it goes.
Great.
All right.
Any other questions? I think there's a lot of questions they're just too shy to ask.
Yeah, well, and if anyone, I'm sure that emails and stuff are being shared. So if anyone has anything or any advice or anything like that, we would both be happy to take a look at that.
Okay. All right. So we have one last talk, and our presenter is Gheorghe Ponta. How you doing, Gheorghe?
Hey, how are you? Can you hear me?
Yes, we can hear you. Gheorghe is from Romania, and he earned his geology degree. Oh, my screen just went away. From the University of Bucharest. He worked at the Geological and Geophysical Prospecting Company and Institute of Geology and Geophysics in Bucharest. He is now in the U.S. He used to work for P.E. Lamoureux as a project manager for groundwater and water-related things. And he now, in 2014, joined the Geological Survey of Alabama, working in groundwater assessment programs. So he's provided specialized support for environmental investigations in karst terrain in the U.S., Romania, Honduras, and Thailand. So, Gheorghe.
All right, can you hear me?
Yes, and we can see your screen too.
Okay, thank you. This way, my name is Gheorghe Ponta. I'm with the Geological Survey of Alabama in the Groundwater Assessment Program. The title of my presentation is Monitoring Karst Aquifer in North Alabama for the Protection of Sensitive Aquatic Biota. Alabama, we're an area about 135,000 square kilometers, is located in the southeastern part of the United States. Of those, only about 35,000 square kilometers are karstifiable rocks, mainly limestone, which represent about 25% of Alabama's territory. All these 4 caves were allocated in the northern part of Alabama, close to the Tennessee state line. All the 4 caves also, they are located in the highland rims and Cumberland Plateau physiographic regions. Key Cave, one of the, has been designated as critical habitat for the Alabama cave fish. The cave fish is here, which is known only from pools within that cave, an Alabama cave bat. The aquatic fauna in the second cave, Cathedral Cavern, is diverse, although none of its members are currently afforded protection. The Alabama cave shrimp population, you see the shrimp, it's a little bitty one, and water quality in Bobcat Cave have been monitored since 1990 and in Matthews Cave since December 2019. The Tuscumbia darter, which is here, it's a fish species found in Niagara Spring, which was been monitoring since December 2019. All these 3 sites are on the Reston Arsenal property, and our contract is between GSA and the Department of Defense. Groundwater studies in all these cave systems and spring have been conducted to determine the recharge area, aquifer characteristics, and water quality data to protect the water resources that support these species. Water levels, specific conductance, and temperature data have been collected using data loggers to evaluate document flow condition and seasonal flow variability. All these rocks where these caves are located are Carboniferous rocks, or on US terms is Mississippian rocks. The limestone and the Fort Payne Church we are going to talk about, these caves are laid down in Fort Payne Church, Tuscumbia limestone, Mount Eagle, Bangor, and Pennington Formation. This is a pretty large variety of rocks from in North Alabama, from pure limestone, we are almost 100% calcite, to dolomitic limestone and silicious limestone. Silicious limestone is mainly close to the Fort Payne shaped area. The limestone itself are light gray in color till dark gray, very finely crystalline, very massive most of the time, and we almost non-existent primary porosity. The primary porosity we are using in our calculus is about 3%. In this way, the major storage and flow in the Karst aquifer located in these rocks are along fractures, vogs, cavities, and bedding plane. The bedding plane in the northern part of Alabama, it's almost horizontal, is dipping towards southwest about 5-6 meters per kilometer. Another picture, we are bluff along the major highways, Highway 72 in Huntsville, Alabama. We have the same horizontal bedding, and here you can see some interesting epikarst features along that main road. Key Cave, it's located, like I said, close to the Tennessee River in northwestern part of Alabama. In Key Cave, I took a picture a couple of weeks ago when I was with a group of biologists, the co-authors of this paper, to count the number of bats in the cave. I took this picture when those folks are counting about 1,100 to 1,200 bats per minute. And they did it for about 2 hours. In this way, I guess there are quite a few bats in that cave. And this is one of the reasons it's protected. In this cave, we install a transducer, OTT hydromet transducer, and the end of it, it's in this PVC pipe, and in this top, it's a device which transmitting the data continuously to our office. It's a real-time monitoring well, or let's name it well. We have temperature, conductivity, and water level data. Also, in the same area, we are monitoring 2 additional wells. domestic wells. This is located about 4 kilometers north of the cave. This one is about 1 kilometer north of the cave. Also, we have a rain gauge installed, and the location of those formation of those units are here. Here, where is this yellow arrow? It's the entrance of Key Cave, the first well, the second well, and the rain gauge. You can notice on the geological map we have numerous sinkholes. The sinkhole was located with a LiDAR. Definitely, there are a lot of more little sinkholes is not showing on the map. And based on the dye study performed by U.S. Fish and Wildlife and Tom Early in 1990s, and more recently, like if it's correct, in 2000 by USGS, they defined the recharge area of Key Cave Karst aquifer to be about this size, based on the dye study which were performed. Key Cave, it's a water table cave. The majority of the year, or majority of the time, all the water, it's a pool water, and it's part of the phreatic zone. And only after heavy rains, what happens probably once in a century, but occurs last year when we have about 20 inches of rain in less than 2 months, from phreatic zone cave became vadose zone cave. We have this stream flowing through the cave passages and surfacing at the land surface almost on the Tennessee River. All this data, which were collected manually and electronically with all those devices, are showing on this graph here. On the bottom graph, we have the rain data from our rain gauge. The red dots is the time when we sample those, collect water quality samples. In the middle graph, we have the water level. This graph on the top, it's the well located about 4 kilometers north. The red line, it's the well located about 1 kilometer north. And here you can see a blue line, which is the water level in Key Cave, and a green line, which is almost overlapped with the blue line, is the water level provided by the Tennessee Valley Authority from the Pickwick Reservoir. In this way, the cave being located that close to the Tennessee River, it looks like that's an interconnection between the lake or Pickwick Reservoir / Tennessee River and the cave. The next cave, which I'm going to present briefly, is Cathedral Cavern. This one is still in northern part of Alabama, about 8 kilometers from the city of Grant. And here we have only one single pressure transducer installed in the cave, about 1 kilometer from the cave entrance, and a couple of just one pictures about the cave. This cave is pretty spectacular, probably one of the nicest cave in the southeastern part of the United States. Here, what happens in the middle of the map, that is the Cathedral Cavern. North of Cathedral Cavern is this spring, which water is going underground, is going through the cave and is surfacing in Cathedral Cavern cave spring. Here it's a cross section, a geologic cross section, which what I showed you before. I presented on the geologic map, and here we have an extensive cross section, a hydrogeologic one, where it's the cave plus the Anderson well. It looks like the Anderson well actually is measured the water level in the phreatic zone, and as today we cannot see any connection between the stream going through the cave and that particular well. Here's a picture, so you know the spring upstream the cave is disappearing underground in the dry season. In the wet season, it's a little bit different. The previous picture is right there, and here is the final spring. Like I mentioned before, here we have another rain gauge. Here's the transducer installed on the bridge on the cave. It's about 10 meters from here. A couple of times a year, the water is going up about 10 meters and it's flooding parts of the cave. Here, we don't have an option to transmit the data via AT&T. We have to go there once a month to download the device. Here is again the same type of graph with all that rain data, water level data, and conductivity. The third site was on Reston Arsenal, where we have Matthew Cave, Bobcat Cave. Here is that site, and my part of the project was this spring here. It's a Yaya spring, which is monitored continuously to preserve this little fish, which is only about 2 centimeter long, the Tuscumbia darter. For this part of the project, I have the observation, the Matthews Cave and one of the wells, one of RS062, which is in that, very close to that cave, and a second well over here just north of Yaya Spring. And my biologist colleagues also, they monitor the same Matthews Cave, the Bobcat Cave, plus the other, plus William Spring. Here, like a PHP cave, we have a transducer installed in the cave, and on this graph, it's showing all the data. If you have any question about this data collected, just contact me after the presentation. Here, it's the graph provided by the biologists, where they have under observation monitoring the Bobcat Cave for over 30 years. We have the rain data, the water level data, then the specific conductors and temperature. On the temperature, I mean, it's not easy to see it. It looks like in the last 30 years, the temperature is moving up about half a degree to 1 degree, which is very possible related to the climate change. We have generated a cross-section of several, but I'm presenting only one in this area. You know, like I mentioned before, the bedding, it's almost horizontal, dipping southwest. And on this map, where these dots are located, I'm going to show you on the cross-section. In those 4 points, in Matthews Cave, Bobcat Cave, Yaya Spring, and one well, we collected 4 water samples for carbon-14. And it was interesting to find that these 3, the caves and the spring, the date, you know, the water is about 1,700 years old, and in the well itself, it's about 17,000 years old. And, you know, based on the main item for my project, I have to define the recharge area of the Yaya Spring, which here is the Yaya Spring, and you can see based on our finding, the present finding, and all the information provided by different folks, that is the recharge area of the spring. And that's about it. Thank you very much. And all this work was possible. Fish and Wildlife and Department of Defense and the Cathedral Cavern State Park, and for sure with the Geological Survey of Alabama. And thank you. If you have any question. Hello?
No questions?
Okay, no, you know if you can hear me.
Oh yeah, we can hear you. And people are here, I can see them, so don't worry.
Okay.
Well, if nobody has any questions, George's talk was our last one for this afternoon. So I want to thank all the speakers for making this a really great session and making some really interesting presentations.